Confirm you can get the audio. Can you get the audio? Jacqueline, can you get the audio? Confirm you can get the audio. Confirm you can get the audio. Hello? Maybe network connectivity on your side. You can check network from your side so that we can proceed. You can check the network from your side to allow us proceed. Yes, is Jacqueline there? Jacqueline, are you there? Fantas? Mudhini? Yes, confirm you can see the screen that we have there. Yes, so the unit is analog electronics, or basically what we can call basic electronics. Analog electronics, or what we can basically call basic electronics. What we're going to look at is a mixture of a bit of chemistry and physics. Just trying to put together the operations of electronic components or electronic equipment in general. And our concern is going to be more on the electronic equipments related to computers. That's really what we are more concerned about. So we're going to draw our foundation from physics and chemistry to understand the electrical theory, understand operations of different electronic components, both passive and active components, what make up a circuit board. I will also look at semiconductors. We look at diodes, the operations, how they are formed, how they produce semiconductors, how they are fitted together in the power supply units of different electronic components or equipments. So we're going to introduce the foundation so that we can catch up, all of us, those who did physics in high school, those who did not do physics, chemistry, and all that kind of group. So we begin from the basics and then we bring everybody on board. Then we can move to different stuff. I hope you can see my first slide. Electrical theory. Electrical theory. So of course, electrical comes from the word electricity. That's a familiar word that is impossible to do without. The usage spans from households to the industry to within the economy, just around the economy. And the generation of electricity is converted to different forms using different devices. So on my slide there, I've given quite a number of examples that you can also put down how the generation is done. We have electrical outlets in our houses. Okay. We have the batteries, which run most of the portable devices. We have lightning as a source or as a result of collision between what we'll call later the plates of a capacitor. Okay, so from a thunderstorm, electricity in form of lightning can be generated. So I'll be posting on some slides so that you just take what is important for you, especially slides that we'll be talking about scenarios, we'll be talking about different analogy, trying to explain how the whole concept of electricity and its operations are concerned. Okay, so some of the slides I'll just pause, you pick what you feel is of use to you, then we proceed ahead. Okay, so the source of electricity I mentioned earlier is we have outlets in our homes. We have batteries that can produce electricity. We have generators. Of course, the type of electricity that is going to be produced is going to vary from the type of source that is producing it and to exactly where it's supposed to be used. So some of the uses of electricity are provided there. We have electric motors turning electricity into motion. light bulbs, turning it to light, computers doing that to produce information, and TVs and speakers are doing the same to produce pictures and sound waves. So basically, that's a transmission that occurs when electricity is generated. So we do transmission from that particular source of energy to produce different kinds of output. Okay, produce different kinds of output. So a continuation of the production of electricity and how it's being used at different stages, X-rays, radios, and so on and so forth. Basically, all those electronic equipments make good use of electricity to produce different types of outputs. Okay, so that's basically a recap on how important electricity is, how it serves the modern generation, how it serves the modern generation. So these are basically historical perspective of what the whole unit is going to entail. Yes, so what is this electricity? So we go back to periodic table, we go back to issues of bonding and structure, we go back to charges, okay, and what makes up an atom, okay. So the slide there, you can see an atom, and inside an atom we have three items. We have electrons, we usually have protons and neutrons. That's what makes up an atom. But of our greatest concern is the electrons, because going forward, what electron does inside an atom is going to be very important to us. Okay, so we say electricity starts with atoms. Okay, with electrons, not atoms. Electricity starts with electrons. And where does electron come from? It comes from an atom. I'm sure at Form 2 level, you must have captured this scenario where you get to know atomic number. Okay. So that's the structure of an atom. That's the structure of an atom. I hope you can be able to see it from your side. Okay, so the balance between the electrons and the protons is what we call neutrality. That's when we say there's a neutral charge. Okay, there's a neutral charge. So I hope you can be able to see outermost layer or energy level. You can be able to see protons, electrons, the total number. Okay, when they balance the way they are, that's when we have neutral charge. We have what we call neutrality. Then, of course, in the outer layer, where we have the electron that can be dislodged with a lot of ease, we normally call it the valence electron. That's what we're going to differentiate between different materials as far as electricity conduction is concerned. So that's the structure of an atom. That's the structure of an atom. And I'm sure we all remember how the classification was being done in the periodic table. It's based on those number of electrons that we say copper is in group 2 or is in group 1. We say silicon is in group 4, and so on and so forth. Okay, so the number of electrons in the outermost energy level will still remain a very important aspect for us as we try to learn how bonding is done. So we introduced the concept of insulators, conductors, and semiconductors. That should be a very simple concept. We know why insulators do not conduct. We know why conductors are in a position to conduct, and we know semiconductors are material in between. That's basically is because of how tightly the electrons are within the energy levels. Okay, that particular force, the attraction force between the inner nucleus and the outer electrons, will define whether we have mobile electrons or we don't. So you will. My slides are loading a little bit slower, but it's fine. Yeah, so that's elements. We all know the magic number 8 as far as periodic table is concerned. So elements with more than 4 electrons in the outermost energy level or rings will make good insulators, because the electrons remain intact. The electrons remain intact. So the bigger picture here is mobility of the electrons. If the electrons are immobile, we have an insulator. If the electrons are mobile, we have a conductor. Then we have this major magic material called the semiconductor that is going to be in between. That's really our area of interest. The electrons, the insulators and conductors, those are very far apart, and they are not of interest to electronic equipments. So an explanation on the same, you can just go through that and pick the relevant examples. A big word here, a big word there in form of free electrons. Very, very important. Free electrons. And that's what makes up conductors. That's what makes up conductors. So the concept of whether to gain or lose electrons is displayed there. Now we all know how that is being decided upon. If I need 3 electrons to attain the stable state, I better gain than lose the 5 that I have. So that's a concept I'm sure most of us are really familiar with. Okay, so we've talked about conductors. We say that conductors needs electricity needs conductors to flow from one point to another. That push, what we later refer to as the electromagnetic force, the EMF, is really important as far as the movement of electrons is concerned. So we are saying one way to do that is by use of a generator. Okay, one way to do that is by use of a generator to ensure that there's electricity. And remember, electricity only flow if electrons are in a position to flow. I'm sure we all are aware of that. So generator can be used to push, just the same way the water pump works. Okay, generator will do that by the with the help of magnetism. So you can just go through that slide and see the scenario of how a generator can be used to get electrons moving or to push electrons. So that's basically a scenario. The graphical pictures, you can be able to have a look at it at your own time. Maybe once we upload the presentation plus the slides, you can just have a look at how the operation is supposed to be done. Internet.
You are currently the only person in this conference.
Forgive my network. Yeah, we can proceed. So I was talking about the graphics. You can have a look at them at your own time and be able to see what exactly is going on. Okay. So that's the scenario where I'm saying a generator can be able to drive or push the flow of electrons, just the same way the water pipes or the pumps will be able to do to the flow of water. So that scenario or analogy, you can have a look at it from a different at a different time once the upload is ready there. So it's still a different time. Yes, so a very important slide here is introduction to SI units of measures, the standard units for electrical circuit and the related unit of measurements around it. So we say that the number of electrons flowing is called the amperage or the current. So that is where we derive the SI unit for current as amps or amperes. Okay. Then I mentioned earlier on EMF is pushing electrons to flow is what we call voltage. It is measured in volts. Okay, so you'll hear those two words moving together. So 1 amp basically means this number of electrons. So you can check that. Means this number of electrons that are flowing. Okay, so when you talk about 1 amp, what you're trying to look at is 6.24 times 10 electrons that are moving through a wire every second. Okay, so time is a very important factor there. So volts is voltage and amps is current. So that's how we get the true relationship between those with the summarized relationship between voltage, current, and resistance. Okay, so these are an analogy. You can read them on your own at a different point. Okay, you can read through that scenario. So this word, we're going to use it quite often, load. Okay, so when we speak about load resistor, what we are referring to is any of those devices that will consume electricity. Okay, so when we'll be balancing our circuits, or we'll be testing our circuits, we'll say, we'll introduce RL. So RL will basically mean load resistor, any of those devices that can consume electricity. So that word load, take note of it. So when we use it later, you'll still be able to remember exactly what we were talking about. So that's the flow of electricity. It's basically a scenario. So you'll have a look at that maybe at some point and be able to see is a continuous of how the pushing of electron happens. Just a continuous of how the pushing of electrons happens. So this scenario here, this diagram here, to the previous slides, you can check it at your own time, is basically how battery discharges and charges. We'll look at the same scenario in capacitors. When we'll be looking at capacitors, how we charge a capacitor, how we discharge a capacitor, we'll repeat the same scenario there. So you can just have a look at that maybe at your own time and see what happens. Now, these three quantities will move the concept of electronics. Those three quantities, okay, it will move the concept of electronics. So we're saying if you get volts times amps, you're supposed to get watts. And this brings to the practical view of what really happens in these power outlets. What do you mean when you talk about that? So we are saying at an average, we bring on board 120 volts. Okay. When you look at the power supply sections of different devices, you'll find a transformer there that will do the step up and will do the step down. Later, we'll be looking at how rectification is done. How do we now? Chepkeru is telling me can't see the diagram. The diagram I was just flipping over. You can have a look at it later. There are a number of diagrams that try to put a graphic on how the discharge and charging of a battery happens. I was just flipping over that particular diagram. But my concern is here. Now, voltage, current, and resistance. And I'm saying there's quite a lot that happens from generation of power coming to your house. There's step up, there's step down, there's redistribution, and so on and so forth. So at your, the outlet within the living rooms is 120. Okay, but now we have the transformer within the power supply section of different devices to do the step up and the step down. Okay, and I was mentioning that then we have diodes to do the rectification to ensure that the voltage coming in is very stable and steady type of voltage that will be able to service most of the electronic equipment. So we are saying if you do this computation, you're supposed to get watts. Okay, if you do that computations, you're supposed to get watts. So if you plug in an electronic device that draws 5 amps, then we say it is a 600 watt. Okay, we say it's a 600 watt. That means the 120 we are talking about here, you multiply by the current to get the watts. From your basic physics, you should be knowing the quantity we are trying to compute here. You should be knowing the quantity we are trying to compute here. So the same happens to bulb, 60 watt bulb. What do we mean by that? 60 watt bulb. What do you mean by that? It's type of a bulb that will draw half of an amp. Okay, so it's kind of going with 0.5 amperes. Okay, so that's basically more illustration on how these components interrelate together. So this is something that is a practical use. You can just read it through and find out. So you can see that computation there, basic maths from that end. Okay, basic maths from that end. So we know what kilowatts are, we know what watts are. That's power now. That's the fourth quantity we are introducing: voltage, current, resistor, and power. So if you give them standard symbols, then Ohm's law comes in. If you give them standard symbols, then Ohm's law comes in. So we say voltage is V, and we know what voltage is. We've said it is the push that push the electrons to flow. Okay, we know what resistance is supposed to be measured in ohms, basically trying to stop the flow of electrons. That's what we call a resistor. Okay, so we say that the mathematical formula that relates the three things. The mathematical formula that relates the three things is, if you want to get current, pick the voltage and divide by R. Something important to get note of is this. We have that small r. Later, we'll be talking about the capital R. Capital R is the external resistance. Small r is the internal resistance. That is resistance that exists in a material as a result of its atomic components, or what we call the geometric properties. Okay, so because of the way the material was manufactured within the manufacturing industry, we have this small r here. Okay, so small r is internal resistance, capital R is the external. That commonly will be we'll refer to it as the load resistor. So this is just a scenario on how the balancing is. So we've seen here the direct proportionality and the indirect proportionality. That will means that when one goes down, the other one goes up, and the same happens. So like this statement here, increasing the voltage will make more current flow. If you are dividing V by R and we increase V and nothing happens to R, mathematically it means that the outcome, which is I, is going to be higher. And the same happens here. So is an inverse proportionality, is an inverse proportionality between I and R. I and V is direct proportionality. I and V is direct proportionality. So that is just a still illustration on what happens there. So I'd mentioned earlier that depending on where you are drawing your source of power, then it will always come in different dimensions. So we have two types of currents. That is direct current and alternating current. And we say batteries, fuel cells, and solar cells all produce a DC. All produce a DC. Okay, the reason here is this. The reason here is this. There's a reasoning behind that. Why do we have batteries, fuel cells, and solar cells producing direct current? It is because of the polarities, the way they are addressed. Okay. Then we say the power that comes from a power plant, the power that comes from a power plant is an AC alternating current, is an AC alternating current. And it's because the direction of the current reverses. Direction of current reverses. at a speed of 60 times per second. That means we are taking into consideration the 120 volt source from the power outlets. That's why you see USA being mentioned here. That's why you see USA being mentioned here. So most of the time, this type of current something has to be done before this can be used in electronic components. That's why you see this, the DC, you don't need to convert the battery cells, so you don't need to convert the power that is generated from there to be able to make good use of that power. But for AC, we need something to stabilize that type of current for it to be able to be used with our electronic devices. So there is really a big industrial advantage here. There's really a big industrial advantage there. That is what you always see from the power generating companies. There's some financial benefits in transmitting high voltages for a longer distance, Okay. Then, of course, when it comes to your residential, there is the transmitters, or there is the transformer that will do the necessary reclassification for that particular voltage before you can be able to consume it as an end user consumer. Okay. So there is a business example here. Just read it through. Most of the time, such slides you just go through by your own because I won't be able to do the maths. I won't be able to do the calculation. You go and check the use of ground fault circuit interrupter. Go and check the use of ground fault circuit interrupters in power outlets. Okay. Now, so the other concept that is very basic is grounding, earthing. So I will not be able to go to that. Before we can just have a look at that, what is the relationship between charge, Q, current, I, and time, T? What is the mathematical relationship between those three from your previous class? Anybody? 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 Now, so if you divide the amount of charge passing through a given point with the time, okay, that is Q over T, then you get a definition of current, another definition of current in relation to charge and time. So if a charge of 1 coulomb passes a given point per second, then we can define what we call 1 amperes. So another relationship that also exists is that Q over T is equals to yes. So having a bit of issues with my connection, but well and good. Okay, so that is what I was saying. So Q is charge measured in coulombs. Time is measured in seconds. and current is measured in amperes. So you can tell what 1 amperes is supposed to mean in terms of charge and time. So if Q is divided by T, then we know we are talking about coulombs per second. Coulombs per second. Okay. So that's another relationship that is part of current. If we forget about the voltage and the resistance. So I was saying that the final aspect of definition of terms or introductory part is electrical grounding, what we commonly call the earthing. Okay, basically what we're doing is trying to ensure that excess flow of electrons is passed to the ground. Okay, what we call the neutral. Okay, so if you in your house or somewhere in the living room, there are always those neutral wires that ensures that excess electrons are supposed to be passed to the ground. You check on those electric poles outside there, then you'll always see a wire that is really pushed to the ground, okay, about maybe 3 meters or 4 meters down there, just to ensure that excesses of electrons can easily be passed to the ground. So that's what we call electrical ground. So you can see the example here. Okay, so you can see that simple photo there, trying to display that. Another one here. Okay. So the grounding is done, or the earthing is done about that particular distance, standard distance, depending on which country you are, and of course the power supply provider. Yes, so that's what the whole basic definitions is all about. So Ohm's law comes in and reaffirms those relationships as mentioned there. Ohm's law comes in and reaffirms those relationships as mentioned there. So we know what volts represent, we know what currents represent, we know what resistance represent, and we know the flow of current is opposite to the flow of electrons. We know basic representation of an atom. We know why elements are in different groups in the periodic table. Group 1, 2, 3, 4, 5, and so on and so forth. So when we'll be talking about silicon, we know exactly why we choose silicon as one of the elements that we can use in building our semiconductor materials. Okay. Any question as far as the introduction is concerned? So all that we've done today, or what we've done so far, is not part of our syllabus. Our syllabus is going to begin at electronic components, capacitors, resistors, and so on and so forth. So that is not part of what we are supposed to be doing, but I just brought that concept up to try and bring both of us in on the same table, so that when we say capacitance or resistance is equals to VI, we all know what VI is all about. Yes, any question as far as that presentation is concerned? Swali, as far as that presentation is concerned? So in our this electronic class, some of the videos will not go live, will not be doing live. I'll do some recordings so that there are mathematics that are coming, so there's some calculations to be done. Okay, so I'll do some recording in advance with those calculations. Then when you go live, we can just be watching that calculation and then ask questions where necessary. It's going to be very important for us to go that way because sometimes it's going to be a little bit of a challenge to do the mathematical calculations on my screen here. Okay. Yes, any question as far as that presentation is concerned? Swali? Chepkirui Naomi, are you there? Chepkirui? Jacqueline Wangui? Lennox is there? Nasike? Mudini? Philmon? And Teddy? Great. So any question? So I'm done with the introductory part. Next, I should be moving to resistance and their circuits, or what we call the electronic components, where we have passive and active components, So that's the next session that we are supposed to move to. Now, what I would love you to do meanwhile, study bonding and structure. Study bonding and structure. Try to know what covalent bonds are. Okay, try to know or understand what covalent bonds are. Try to understand the valence electrons in detail, or what we call the compounds. Okay, so what do we mean when we're talking about a compound? They'll really be able to help us moving forward to understand with a lot of ease the concept of semiconductors. Okay, I would also love you to go and look at the differences and examples of passive and active electronic components. Passive and active electronic components. And of course, define or get to know what we mean when we say printed circuit board, PCB. What do we mean when we're talking about printed circuit board? Printed circuit board. If there's no any other question, allow me to end the session for today. End the session for today. But before that, let me just know. Let me just know if there are colleagues of yours that have enrolled for the blended learning and maybe are not part of this class. You can just check on the participant view for those who are present. Okay, can just let me know so that I'll be able to know the expected number, just to help me put together some statistics. Anybody you know that is not present here? Okay, so if there is no any other concern, then I call the class to an end. You can discuss among yourselves for some few minutes, then we can end the meeting. On the other side, you're also free to exit, and see you next week, and have a lovely weekend.
You are currently the only person in this conference. You are currently the only person in this conference.